Okay, so yeah, so once again, heat equals work done by friction. Rub your hands together and you know that. So then the heat gained by the aluminum block is mc delta T. The work done by friction, work is simply force times distance, right? Force is friction. That's the thing that's trying to stop the block, that's slowing it down. So the force of friction, we know that from our formula sheet, is just mu F sub n. For this block, F sub n is mg cos theta. So I substitute that in and I get mc delta T is equal to mu mg cos theta times L, right? Or force times distance. And then I just solve that for delta T and get my answer. Okay, questions from that? Okay, so if we go to part two says, what is the efficiency of this system and how much heat was lost to friction? So efficiency is what over what? Yeah, it's work out over energy in, right? That concept. And what is the energy in? Yeah, so in this, in this case, what is making this happen? What is making the thing slide down the incline? Gravity. So this is like the potential energy of gravity. You see that part? What? No? Why does the block slide down the hill? There you go.
Oh, this is the bottom part.
Yeah, what kind of energy? Yeah, this is the bottom, just the bottom. And then what is the product? What was the work out? Yeah, no, what we're talking about there is, we're talking about this is the efficiency of the mechanical energy being converted to heat. So this is like Q on top. So this is one of those things where I kind of mentioned the other day, don't get stuck on efficiency being this specific formula of work out over energy in. Or like, whatever. Efficiency means what did you get from what you put in, right? And that makes sense to you, I think. What did you get from what you put in? Efficiency in a car is miles per gallon, right? So efficiency is a concept, not a specific formula. Now, yes, you do have a formula that can be used in certain cases, but it's better if you have the concept in your mind, right? So in this case, we're sticking with the correct units, and this is joules per joules, right? Joules over joules. That cancels. We get a percentage, efficiency percentage. But what we're saying here is how much heat out of it did you get from the energy that you put in? And the energy that we put in was at the top. So what is the efficiency of the system and how much heat was lost due to friction? Yeah, so then we can say, or actually, you know what? Let's do this. Instead of heat, sorry, I'm getting a little twisted around. This thing goes down this incline, right? When it goes down to the incline, what lets us know that gravity did some work on this block? Yeah, because it's moving right here. It's got a velocity. So somebody said velocity earlier. Or did they say kinetic energy? Yeah, kinetic energy. So what we have to do, it's not the heat, because the heat is actually the waste, because the heat goes into the block and disappears. What you got out of this thing was the velocity at the bottom. So it's like kinetic energy, like that. Sorry, I got a little ahead of myself. Does that kind of make more sense? It's like you get out, like what's the point of letting something go on a hill? So it goes faster, right? So it moves, it slides, it goes quick. That's why that's why you put soapbox cars on a hill. You want to watch them race down the hill. So here we put the block here, it slides down. So at the top it's going to have some PEG. At the bottom it's going to have some KE. This is a non-conservative system because of the friction. Does this make sense to you? Does that make sense? Remember non-conservative energy systems? So what we're doing, this looks just like a thermodynamic energy system. This is QH, this is W, and this is QC. So now it's just a function of figuring it out. We just figured out over here, well, I guess there's a bunch of ways we can do this, I guess. The PEG is easy. That's just MGH, right? And in fact, rather than MGH, because do we know the height? I don't think we know the height. I think we know mgl sine theta. Because that's L and that's theta. So H is L sine theta. So that's the PEG. Now how do we find the kinetic energy at the bottom? There's a whole bunch of ways that you can do that, right? You could calculate, if we know, like we can calculate the acceleration down the hill, and then by calculating the acceleration down the hill, we could figure that out. You could also play this game. You could say KE is equal to PE minus WF. Does that make sense? Any questions there? So then if that's true, then I can put that up here. PE minus WF. Do I know WF?
Yes.
That's WF. Not to be confused with WTF. So anyways, sorry, that was a dumb joke. So my efficiency is going to come out to be, actually, oh, look at that. That's kind of neat. If rather than filling this in, look at this. If I put PE here, then I get 1 minus WF over PE. So then here it's 1 minus, and then this is going to be mu mg cos theta times L, and then this is going to be mgl sine theta. Hey, look at that. mg cancels, L cancels. Ooh, this is pretty fun. All right, and you get 1 minus mu cos theta over sine theta. That's pretty neat.
Wait, how'd you get the one? Where'd the one?
Because it was PE minus WF over PE. So isn't this the same as saying PE over PE minus WF over PE? Yeah, that's fine. Good. Like the questions. Good. And then somebody can do this. Was the angle 30?
Yeah.
Oh, that's good. Was mu 0.5? Okay, so then that means this is 0.43 over 0.5, which is around 0.7. So this is around 0.3 or something. What do you get? That's a guess.
0.43.
Oh, terrible guess. 0.43 or 43% efficiency.
Oh wait, total? Sorry, I thought you meant the mu cos theta.
Oh, okay. Sorry.
It's like 0.1.
Point what? 0.1.
0.1. Unless I don't know how to do math.
If this is 1 minus 0.5 times 0.866 over 0.5, oh, duh. I forgot. I can just cancel the 0.5s. Yeah, you're right. It just comes out to be 0.14, close enough. 134, technically. Or 13.4%. Okay, so once again, just to review, what we're doing here is we're saying efficiency is what you get out over what you put in. What did we get out? We got kinetic energy in the block. What did we put in? We put in potential energy of gravity. So now after we know that, the rest of it is just algebra stuff. Because then we're saying PE minus WF is equal to KE. So then I put that over this, and then from that I get 1 minus WF over PE, plug everything in, and get my answer of 0.134, or 13.4%. All right, we move on. Part 3. If the waste heat of the system, the heat loss to friction, so the heat loss to friction was, the work done by friction. So if the heat loss to friction went into a volleyball, okay, so the volume of the ball is 4/3 pi r cubed. The radius of the ball is 0.10 meters. What would be the change in temperature? So basically here we're saying, once again, we're using this, right? We're saying the heat that goes into the air is equal to the work done by friction. So then this is going to be mc delta T, and this is going to be mu mg cos theta times L. So once again, mass is not an issue. And we simply, and I give you the specific heat of air, so that's fine. And so they want to know what would be the change in temperature. So once again, delta T is equal to mu g cos theta L over C. Oh, what a retard. I made a big mistake. What'd I do? What is this the mass of? The air in the ball. It doesn't cancel with this. That's an aluminum block, for God's sakes. There we go. Okay, sorry. I have to go back here. This is mass of the air, and this is the mass of the block. Okay, so, I mean, same thing. I just still get delta T equals mu mbg cosine theta L over mass of the air times specific heat of air. And then what you have to do here, density is mass over volume. So mass is density times volume. So that gives me mu, mass of the block, g cosine theta L over density of air times the volume of the air times specific heat capacity of the air. And then all that stuff's just given. The density of the air I gave you. The volume of the air is right there with that radius. Specific heat of air I gave you. Mass of the block, you know. G, blah, 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 do that. I don't have a calculator. Where's the calculator? Okay, well, let's plug the numbers in so we can kind of see. Mu was 0.5. What was the mass of the block? 150 kilograms. Okay, gravity's 10. Cosine of 30 is 0.866. What was the length? 20 meters? Okay, 20 meters. Then the density of air, and it says right there, density of air is 1.3 kilograms per cubic meter. The volume of the air is 4/3 pi times 0.1 cubed. And the specific heat capacity of air is 1,000 joules per kilogram Kelvin. So there you go. Just whatever, do the maths. So, yeah, I don't know. I don't want to do the math. You can do the math. Then, 4. Woohoo! Look at us. What would be the final pressure of the ball if it began at regulation? So, if the initial pressure of the ball was 1.35 times 10 to the 5th pascals, then what is P final? So we're just taking the change in temperature, which we found, and then plugging it into here. So we can use, we did that, right? Universal gas law and all that stuff? Pivnert? Yeah, okay. So we can use PV equals nRT like this. And then, oh yeah, okay, cool. We knew the 0 degree air. Oh yeah, actually, I don't think we need to do that. Let's do this. P1 V1 over T1, remember this from chemistry? No? Yes? Okay. So P2 is going to be equal to P1 times V1 over V2 and T2 over T1. What does V1 over V2 become? That's 1, because it's the same ball. And we assume that the ball doesn't inflate like a balloon. Okay, so then it's just a ratio of the temperatures. And I think they said, wait, T1 was 0. But then if I put 0 here, doesn't that create like a...
Yeah.
So what do I do? Instead of... Yeah, thank you. Whoever said that. Was it Linda? Yeah, nice. You have to make it Kelvin. So remember, 0 degrees Celsius is 273 Kelvin. And that's going to be T1. T2 is equal to 273 Kelvin plus delta T. Where do we get delta T? From part 3. So the part 3 that we just did, take that delta T, add it to 273, and I get my 2. And that's it. Now we can yak about relationships all you want. Yeah. Your plan to delay me has been thwarted. Okay, I'm going to turn this off. I'm not making it disappear.